Thank you. It's Chunmo Zheng from Zhejiang University and a visiting student in Newcastle University. So today I'm here to present our work on intelligent knowledge graph question answering for health and safety hazard management using large language models. So health and safety is important in construction industry as the accidents are persistently occurring. And in safety management, the managers need to analyze safety hazard in a timely manner and formulate the measures to reduce accidents. And in the construction industry, it produces large volumes of safety data as the accident case report, the risk registers, the regulations, and they are in diverse formats and sources. So this leads to significant interoperability issues. While most safety hazard management measures still rely on manual ones, which is time-consuming and inefficient. So existing researchers use text mining to extract and analyze information from unstructured safety hazard text. Typical research include using machine learning and deep learning to classify the accident types or to extract certain factors from the text. And they also standardize and visualize this information in a graph database. So existing researchers, they only focus on one type of safety hazard text mostly, such as the accident report. But there are other types of knowledge, the risk register, the regulation, etc. So with the current knowledge modeling, the interoperability issues still exist. And second, they neglect the interaction between the construction manager and the safety hazard knowledge. So in this case, the managers are the users, and these texts are the source of the knowledge base. And when the user requires an answer from the knowledge base, there always lacks a direct way to fetch the answer. So intuitively, we want an intelligent QA system to directly fetch the answer and search the knowledge base. And this is because the safety hazard text is mainly presented in the QA pairs. So in this work, we propose this knowledge graph question answering framework for safety hazard knowledge. In the first part, we construct the safety hazard knowledge graph by integrating different sources merged in one knowledge graph by the predefined ontology. And in the second part, we develop language model-based natural language understanding assistant. It enables the users to search the knowledge graph and return the answer. So the returned answer could be the risk measure or a relevant accident case, depending on the specific use case. So let's first take a look at the KG construction part. So we collect the data from the Health and Safety Executive in the UK, which contains both the structured safety register and the unstructured data, such as the accident case report. And in the case report, they also mention the specific regulation and some other information. So across this text, we model the concepts and the relations are modeled in the safety hazard ontology, where we define concepts such as risk scenario, risk category, the risk factor, the responses, and the case, which is the consequences, and the regulations, standards, etc. So the integrated data is then imported in a graph database Neo4j, which is result in 1,030 nodes, 1,500 relations. So initially, if we want to search the knowledge base, we need to write cipher query manually but we want a more intuitive way to search, to interact with the database using natural language, to support tasks like safety measure generation and accident case recommendation. And this is enabled by the second part, a safety hazard QA system powered by large language models. And in our system, the core module is a natural language understanding module, and which is responsible for translating the text to cipher. So step 1 in this module is safety measure, is intention classification, which we classify the intention into different types and for triggering different functions. So for example, if we have the user query here asking about safety measure in a safety situation, then the intention classification prompt embed this query as an input, and the language model takes this input and classify it into one of the different types. So here it is expected to classify the question to safety measure generation by return 1. And in the second part is the ontology mapping, which it retrieves the subgraph, the relevant part in the ontology, according to the intention. So for the safety measure generation, some relevant concept could be the risk category, the construction activity, the risk responses. So their classes and the subclasses is retrieved for the next step. And step 3 is entity extraction. In the entity extraction prompt, the language model is asked to map the user query to a knowledge graph ontology. The user query is one input, and the retrieved ontology is another input. And the model is asked to output the extraction result in the JSON format. And finally, we will parse these JSON files and generate the cipher query. So here the cipher query is to match all of the risk responses, which then satisfy each of the constraints in the filter. So it will return the responses in the database. We test our method using a natural language query dataset with 192 queries, which covers 2 types of tasks, safety measure generation and accident case recommendation. And it includes 3 constraints: risk category, construction activity, and risk location. So this is a sample dataset, and for each row, we have a natural language query. We have annotation with 3 constraints, and also the answer to the query. And we compare our method with a popular long chain solution integrated with Neo4j, which also transform text to structured query language. And we use the accuracy to measure our system performance. As shown in the table, the long chain solution failed with all 3 language models due to an inaccurate mapping from user query to the ontology, while our method achieved high performance in both 2 settings across 3 models. So to conclude, the safety hazard knowledge graph models interconnected relations between safety hazard knowledge, integrating scattered information in the one unified framework. And by developing a language model-based natural language understanding assistant, it enables flexible and intuitive access to the safety hazard knowledge using natural language. But the limitations still exist in terms of limited dataset, dynamic update of KG, and the lack of more real-world testing. So in the future work, we propose to focus on the three parts mainly. First is to integrate a larger and more diverse data sets from real-world construction practices. And second is to explore automatic ontology refinement and population to reflect the evolving context. And third is to assess our system in both information retrieval and answer generation process. Thank you.